Hey, what's up, everyone? This is Rob, and this is an introduction to statistics for the psychological sciences. This is the fifth lab video, and we will be exploring how to conduct a simple regression analysis using SPSS. So what I've done is I've pulled up our data set from last class on mindfulness and mental health. And what we're going to do, we're going to go through and conduct a regression analysis between trait mindfulness, which is listed here as MAAS. That actually stands for the Mindful Attention Awareness Scale. And it assesses the frequency with which people enter into states of mindfulness during daily life. And then we have a variable called NEO-N, and that stands for the neuroticism measure, right? And so we want to check and we want to see if we can create a predictive simple regression model to predict how neurotic a person might be based on their level of trait mindfulness. And so in order to do so, we have to determine whether or not the mindfulness and neuroticism variables meet the basic assumptions for simple regression. Well, so the first assumption is that there is a linear relationship between the two variables. So to test that, I'm going to go and I'm going to just do a simple scatter plot. And we're going to go to Graphs, Legacy Dialogues, and then Scatter Dot, Simple Scatter, and then click Define. And we have trait mindfulness as our predictor on the x-axis. And what we're trying to predict is their neuroticism. So we put that on the y-axis. It's as simple as that. We click OK. And we can see, yeah, it does look like you could draw a line. It looks like it's going to be an inverse relationship here, or a negative correlation, meaning that as trait mindfulness increases, people tend to demonstrate lower levels of neuroticism. That sounds healthy. And so we can see this doesn't look like a curvilinear relationship. It looks like you could fit, you could draw a line of best fit in here. So we can assume that it meets the assumption of normality. So now we want to, or the assumption of linearity. So now we want to assess the assumption of normality. So to do that, we'll go to Analyze, Non-Parametric Tests, Legacy Dialogues, and then one sample Kolmogorov-Smirnov. And we're going to just put in trait mindfulness and neuroticism. So again, this is all review. We've done this in past assignments, but it's always good to test the assumptions of the statistical analysis you're going to conduct. So we click OK. And then what we're interested in here is whether or not the test statistic shows that it is significant, right? So if it's less than 0.05 under this significant two-tailed, right, then that means that it's not normal. So this test compares our sample data to a theoretical normal distribution. And if our data is significantly different from a normal distribution, we can say it's not normal. We don't want that. We want this value, the significance value, to be higher than 0.05 because we want normal data. When we have normal data, we're meeting the assumption of normality and we're able to conduct this test in good faith. There would be nothing stopping you from running a regression analysis without normal data. The problem is it's kind of garbage in, garbage out. If you're giving it data that violates the assumptions of the test, what it's going to tell you is going to be just as much garbage as what you gave it. So it's very important to make sure that all the checkboxes are ticked off in terms of the assumptions before you conduct a test. So here we can say, since that we're over 0.05 for our significance value on the Kolmogorov-Smirnov tests, that we are safe on the normality front. Okay, and the final thing that we're going to want to do is we're going to want to assess whether or not we meet the assumption of homoscedasticity, which suggests that there's equal variance in terms of our prediction errors around the line of least fit, or the line of best fit. And so the way you do that, you have to do it by visual inspection. So there's really no like clear cutoff. But when you can do it while you run the analysis. So let's just go ahead and run a regression analysis. So you just go to Analyze, and then you go to Regression, and then go to Linear. Okay, and so here, the dependent variable is the variable that you're trying to predict, right? And so that's your y variable. So the y variable, we're trying to predict neuroticism. And the independent variable is your predictor. And we're trying to predict neuroticism from mindfulness. So we'll take mindfulness and throw it over under independent. And so this defines the basis of our model. But let's go over and look at some of these other options on the right. So if we go to statistics, we want the estimates of our regression coefficients. And we're going to want model fit. And we could go ahead and check descriptives. That'll give us things like the mean and the standard deviation of the variables that are included in our model. Okay, and so click Continue. And then go to Plots. And this is where we assess whether or not our distribution is going to meet the assumption of homoscedasticity. So what we're going to do is we're going to put the standardized residuals on the y-axis. So that's z resid. And then we are going to put the standardized prediction from our model. So what y is whenever it comes out, and we put it under the x variable. And then we click Continue. And that's going to give us a plot of how our errors are distributed about our predicted values. Then if we want, we can go to Save. There's a lot of options here. We're only going to pay attention really just to one, right? So go ahead and click Predicted Values Unstandardized. What that's going to do is for every case in your data set, it's going to make an extra variable that shows you what the regression model would predict their score to be. And so this allows you to see, in units of the raw variable, what regression would have told you about that person. So go ahead and click Continue. And that's all we need here. So let's go ahead and run. And then before we even look at the model statistics, let's scroll down and look at our scatter plot, so we can see that we have the standardized residuals on the y-axis and standardized predicted value on the x-axis. And so since these are standardized, you can assume that these are in units of z, right? And so when we see this, we can see how our residual, how big the errors are across the full spectrum of the values that are predicted by our model. So I would say, there's kind of a gray area in terms of, well, how heteroscedastic does it need to be before we say that the assumption isn't met? Well, I mean, this is kind of rule of thumb here, but this looks pretty consistent. I mean, there is a pretty negative residual out by the predicted value of 2. But, if we took, like, overall, it looks like our errors are pretty normally distributed around our predicted values. So let's go ahead and assess our output. So I'm going up to the top of the output, and you can see, because we requested descriptive statistics, it gave me the mean and the standard deviation for both of the variables in our model. And we can see we had a total of 61 people in this analysis. And then it also gives us the correlations, right? So this is exactly what you would get if you ran a Pearson product moment correlation analysis like we did in the last lab. So regression just gives that to you. And then if we go to the model summary, right, we have R, that's big R. And what this means is this is essentially the Pearson correlation value for how well our model predicts the dependent variable. And so oftentimes, so we have simple regression, which is what we're doing. Simple regression involves one x variable to predict one y variable. But there are other types of regression. So one additional type that's similar to this is called multiple regression. And what that does is it uses multiple x variables, multiple predictors, and all of those can improve our prediction about some kind of outcome y. And this big R value would signify in that context basically how well our model predicted the outcome. So next to it we have R squared, and this R squared value is essentially the effect size, right, or the magnitude of the prediction. And so with one variable, this is going to essentially explain the proportion of variance in the dependent variable that's explained by our model. Adjusted R square, that's what's typically used if you have sample data and you're trying to make some kind of inference to the population. The adjusted R square value kind of, it takes into account that we're making that inference to the population. And so it slightly down adjusts the amount of variance explained. And then here is the standard error of the estimate of our model. So we computed this by hand in the lecture video on simple linear regression. But so this is telling us how much does this model tend to be off on average in its prediction. And so we tend to be off about 0.51 units when we're making a prediction on average. Okay, so let's just go ahead and we're going to skip over this ANOVA table, and let's go to the coefficients. This is where the meat and potatoes are. So what we see here is we see the constant, right? And now this constant is going to represent A, your y-intercept. And trait mindfulness, right? This is your x. And so B here is going to be the coefficient in your equation. So based on this, we can tell that our model is going to be y hat equals minus 0.416 times x plus 3.317. So that is our complete regression equation. And that is really basically it. So what would that mean? What does that regression equation actually imply? So it suggests that for each unit of increase in trait mindfulness, there is a 0.416 decrease in neuroticism. So as someone's trait mindfulness increases, their tendency to be neurotic is reduced. Okay, and so one other thing just for fun, right? Why don't we look at whether or not our values that we predict from the model actually kind of correspond to what we would expect. So to do that, if you remember, we selected in the menu before we ran this analysis that we wanted it to give us a variable with the predicted values from the model. So we can just go back to our data set, and we'll see here we've got PRE_1, and this is a new variable that wasn't here before. And so what this is this is the predicted value that our model spits out for a raw value when given a mindfulness score. So we're predicting neoneuroticism. And so you can see that the actual value is 2.17. The model predicted 1.51. So it's a little lower. Now, for the second case, our model predicted 1.79, but the actual value is 1.67. So that's a little bit more accurate, right? But so you can see how this works. So this is like y hat from the model. So it's as if SPSS took each person's trait mindfulness value and used the model to predict their neoneuroticism value. And this is what it came up with. So you can tell here that our model predictions are not perfect. They're somewhat off, but it's better than if we did not have information about their mindfulness. If we did not have information about their mindfulness, our best guess of what their neuroticism score would be is simply the mean of neuroticism. But our regression model allows us to incorporate that information about the relationship between mindfulness and neuroticism to make slightly more accurate predictions about how neurotic a person will be, depending on how mindful they are. So let's look at something else. Let's do a scatter plot that links mindfulness with our predicted value. And what we should end up seeing when we do this is that the points of our prediction all fall on that line of best fit. So let's go to Graphs, Legacy Dialogues, and Scatter. simple scatter. And we need to take out the stuff that we had here. And to do that, one thing you can do is just click reset here at the bottom, and it'll just reset the whole module that you're currently in. And also, it might be handy to stretch your window out so you can read all the variable names. But so on our x-axis, let's put trait mindfulness. That was our x variable. And we're going to use it, and we want to plot on the y-axis the predicted values that our model gave us. And what we should see is basically the line of best fit. So if we click OK, boom, look at that. They all line up perfect. That represents the line of best fit. These are all the values that were predicted. And you can see that our predictions genuinely do follow that straight line of best fit to the T. And so you can see that line of best fit would likely fit this data. Okay, well, I hope this is helpful. This was a rather quick lab. It's easier to grasp regression after correlation. So I hope this made sense to you, and enjoy.